Hi there, I'm Nick Barraclough, President at AKCP, and I'm pleased today to be showing you around the latest developments in our test data center or our physical twin. So the physical twin is a physical representation of a digital twin. So an industry standard digital twin is a digital representation of your physical data center or facility. And in this case, we're creating a physical twin. So AKCP's central monitoring software creates a digital twin, and we're creating a physical twin of that. So we can actually demonstrate all of AKCP's technologies in a real live environment. So we're not filling it up with servers, we've filled it up with heaters to simulate the heat load that the servers would generate. We've got innovative cooling systems, and we're able to operate our physical twin in different configurations. So we have hot and cold aisle containment, we have a fan wall, we have raised access floor, and so on. So we're able to simulate lots of different types of environments that our customers may have, and we'll be able to produce actual studies as to what is the most efficient way of running your data center, as well as showcasing all of AKCP's monitoring technology and of course our central monitoring platform. So it's been an ongoing project. It's been going on for quite some time to get everything built and designed, and along the way we've had various challenges, but we're slowly getting there. The water piping is almost finished, and also in the last week we've set up a new IT room. So that's an actual real operating server room where we're installing AKCP devices, and that's running all of our in-house demo units as well. So let's go and take a look at the developments that we've got. So here we are in the IT room, or our actual real live server room. We've got a rack here which has been equipped with some AKCP monitoring equipment and also has some operational servers. So on the front of the door here we have the AKCP swing handle cabinet lock. We've got a mechanical key override, but we can also access this with an RFID as well. And then inside of the rack here we've got our actual servers. So these are running various in-house services. So this is our own actual live working in-house facility that we've been setting up here over the past couple of weeks. So our demo units, online demo units, are also in here. So we've got some SPXs, we've got an SP1 Plus and an SP2 Plus here on a DIN rail. And up here I've also got an SPWTS, which is our wireless tunnel server, connected up to wireless sensors that we have in other parts of the facility. So what we're actually doing here is utilizing the AKCP monitoring equipment as it would be in a real situation. And of course it scales, it doesn't have to be one rack. We can do anything from a single rack setup like this, all the way up to a hyperscale, multiple thousands of racks in your data center. So what we've got running on these servers at the moment is our central managing software. So this is where we can bring in all of our sensor data and display it in 3D graphics, graphing, alerts. So this is our DCIM, or data center infrastructure management software, is running on here. It's a clustered system, meaning it's fault tolerant and scalable. So you can see it's actually a cluster here of 5 servers. These are 5 Linux servers, and we're basing this on Kubernetes. So it will scale and is also fault tolerant. So it's a high availability DCIM that we've got running on here, and this is what we use for our in-house development and also for customer demos. So this IT room will have eventually some containment and stuff put in. We've also got some more servers that are being delivered that are going to be running our own in-house backups and so on. So this will be the kind of heart and soul of most modern businesses, is the server rack where all of your data is stored and processed. So let's now go and take a look at the progress that we've got in our physical twin test data center. So here we are in the actual physical twin test data center. This is our hot aisle containment pod, which is the area that we're focusing on finishing off first. It's probably the most complex because we've got multiple different ways of cooling down this area. So we have the fan wall behind me there, which will have a bunch of heat exchangers and basically a hot room behind there. The fans that you see up at the top will be sucking in the hot air from the hot air plenum, and it will then be cooled by heat exchangers that are behind this wall and blow cold air out through those fans. Now we also have as well in-row AHUs, which will be positioned in row here, and they'll be blowing cold air out into the room as this is hot aisle containment. So we'll end up then with a containment of the hot air in the center aisle and this area being cold. And then right up at the top there, you'll wonder why maybe we have this relatively beefy looking structure. It's to support overhead heat exchangers. So we have another method of cooling here where the hot air from the contained aisle in the middle will rise up, go through those heat exchangers, be cooled down, and therefore eliminating the need for the in-rows, giving us more rack space. So we can run this in several different configurations, as I said, and we'll actually be able to run tests backed by AKCP sensor data and CFD analysis that will analyze what is the actual best setup and most efficient way of running your hot aisle containment. So for the heat loads, as I said, we're putting heaters in, not servers. What we're doing here at the moment is wiring those up. So we've got a bunch of switches here. These switches will be rack mounted here at the front, and that will allow us to turn on and off various heat loads. So we've got 3 9 kilowatt heaters positioned top, middle, and bottom. So we've got heater at the top, the middle, and the bottom. And each one of those 9 kilowatt heaters has a 3 kilowatt heating element to it that we can turn on and off individually. So we could run this with various different loads, and we can simulate as well, say some racks where you've got higher density at the top of the rack and lower density at the bottom of the rack. We could turn on the bottom heaters to have only 3 or 6 kilowatts, and we could have the full 9 kilowatt load at the top. These fans here are then simulating the server fans, so they're going to be sucking the cold air through, and they're going to be responsible for cooling down those heating elements. So cold air comes into the rack and hot air comes out the back, just like in a real server rack in a real data center. So let's go and take a little closer look at how we've structured the inside of these racks. So here we are inside what will be the hot aisle, and the heater boxes will be mounted on these shelves here. And you can see we've built a ductwork inside of this, which will direct all of the cold air that's being sucked in straight through these heaters. Without this kind of containment and ductwork, then we would just have bypass air, and the cold air would be going around the heaters and not really cooling them down. So we've customized and built all of this specifically for our test setup that we have here. So every one of these racks has one of those. The rack next to it here, you can see, is also in the process of being wired up. So this is what it actually looks like with those 9 kilowatt heaters installed. So this is the end that is creating the heat. It's simulating the heat load of our data center. Now obviously we also have to have a cooling side of this. What I'm talking about is generating cold air, but how are we actually doing that? Well, we're doing that through a chilled water system and our own proprietary heat exchangers, which increase the efficiency of the cooling system. And one of the reasons why we're building this is also that we're going to be able to demonstrate those improved efficiencies that we are able to get by using our own proprietary patented technology. So let's go and take a look now at how the cold water is going to be distributed around the facility. So here we have 4 pumps. So these pumps will be responsible for moving the cold water around the facility. Behind here we have quite a complex network of pipes and valves, as you can see. That allows us to configure these pumps in different configurations. So we can have all 4 pumps running in series, we can have all 4 pumps in parallel, or we can have 2 pumps in series and 2 pumps in series and put those in parallel with each other. So that allows us to change flow rates or pressures. If we run pumps in series, then we will get an increase of pressure but the same flow rate. And when we run pumps in parallel, then we will get an increase in flow rate but no increase in pressure. So depending on the demands of the facility, we can actually reconfigure this to run in different ways. These pumps are used in conjunction with the large tank you see behind me. So this tank will be kept cold by our chiller that's outside. So the chiller will be circulating water around this tank and maintaining the temperature of the water inside of that tank at our preset requirement. These pumps will then be taking the cold water out of that tank, circulating it around the data center and returning it back to the tank. So we'll be taking cold water out and returning hot water to the tank, and the chiller will be taking the hot water out and it'll be returning cold water to the tank. So the whole system will reach an equilibrium, and we want to maintain an equilibrium in that tank of around 24 degree water or 23 degree water to give us around 24 degree air inside of the data center. Now, it's not the most efficient way of doing things because we are having to run the two sets of pumps. We're running the circulation pumps and we're also running the chiller pump. So we do have another configuration where we bypass all of this and the tank completely, and we only use the pump from the chiller. So that will supply us with enough water to all of the heat exchangers within the system. And if there's more water than's needed, then we have a pressure relief valve which will allow the unused water to return back to the chiller. In addition to all of this, we have a reverse osmosis system that's going to be coming in, which will allow us to produce our own clean water that we can use. And in addition to that, we also have self-cleaning filters which are outside. Let's go and take a look at those. So here we have our two self-cleaning filters. They're not connected up yet, but they've been mounted and they've got the pipe connection on the bottom, but the output not yet done. So basically, we run two of these in parallel with each other so we don't get as high a pressure drop, but one is actually sufficient. So we can run the whole system off of one, which means if one is being cleaned or is out of service, we can bypass it. We have some valves and we can shut off one of these while we service it and run the data center through the other one. These are self-cleaning, which means that they have a differential pressure sensor on the input and the output, and when it senses a high pressure differential, it knows that the filter is getting dirty and therefore it will clean it. So it has built-in scrubbing brushes inside. It will clean off the filter, and then there is a purge through the top where it will eject the dirty water into the drain. So that's how our self-cleaning filter works, and this comes directly after the chiller. So the chiller plant is what you see behind us there. That's a 250 kilowatt chiller that will be producing the cold water. So the first stop for the cold water on its journey to the data center is to go through these filters. After coming through the filters, it will then enter the data center where we have a dirt and air separator just before we enter into the data center at the highest point of the pipe. So that allows us to purge any air bubbles that may have been introduced to the system, and it also separates any dirt that potentially has got past these filters. We do have more air and dirt separators around the system as well. So pretty much before every tap-off point from the main line going into one of the heat exchangers, we are also putting an air relief valve as well. That just helps us to keep the system running without air bubbles, which can lead to airlocks. If we get airlocks inside some of the heat exchangers, it will reduce the efficiency, as those air bubbles will block the water from flowing through certain parts of the heat exchanger. So it's important that we keep air bubbles out of the system. So that will be the job of the air relief valves. So after it leaves here and goes into the data center, we have a main 4-inch line that goes in a loop and returns the water that's unused back here to the chiller. And what we are using is going to go through the heat exchangers that you saw earlier, our overhead heat exchangers, the fan wall, the in-rows, and that's what will be producing the cooling for our physical twin. So thanks very much for tuning in. Don't forget to like and subscribe to be kept up to date with all of the latest videos from AKCP. I do aim to try and get one a week out. It has been slipping a little bit lately, but as things ramp up and we've got more exciting projects going on, there will be more content being created. So again, thanks for tuning in. Don't forget to like and subscribe, and I'll see you in our next video.